Okay, so let's start with MotorSolve. As you may know already, MotorSolve is a package which is used for designing electric motors and generators. So today I'm gonna give you an example of a PMDC motor. So but by that we can actually explain all the panels and settings that we have in MotorSolve in terms of electromagnetic design, and I'm gonna tackle thermal design as well a little bit because we don't really have time, and if you're gonna go into multi-physics analysis, it's gonna be really time consuming. But for now, let's start the project with selecting motor type. So as you can see, we have four general types of motors here: brushless DC, induction motor, switch reluctance motor, and DC motor. In the first one, we can also have generating operation as well. Personally, I think this brushless DC term can be kind of confusing because in industry, brushless DC refers to a type of motor with specifically trapezoidal back EMF waveform. However, in the software packages, we use it as a general term for both trapezoidal and sinusoidal back EMFs. So this library consists of both types, and depending on the winding configuration, you can have kind of semi-trapezoidal shape as well as sinusoidal shape as well. So let's start with the first one, which is brushless DC motor. We selected. The first stage to designing a motor is initial sizing, okay? And initial sizing in actually the classical approach consists of some analytical equations and or magnetic equivalent circuits by means of which we can actually find the rough dimensions of the design that we are looking for, but the inputs to the initial sizing for BLDC motors, brushless DC motors, the three main inputs are the supply voltage, rated speed, and rated torque. So depending on the application and the high-level design requirements, which is usually defined by the application engineer, we can get these values. For example, in terms of supply voltage, it depends on the capability of the batteries. For example, in an application like electric vehicles, batteries can range from, if I'm not wrong, 300 to 150 volts up to 600 or 700 volts. So for now, let's focus on a 400 volt battery pack, and then rated speed. Again, it depends on the motor type, application type, and many different factors. But for now, let's say that the rated speed of the motor has to be something around 3000 RPM. Oh, sorry, there's a noise outside. Let me close the window. Okay, so then we have the rated torque as a high-level design input. Again, it depends on mechanical parts of the system that we are going to design the motor for. But for now, let's say 100 Newton meter, which can be a typical value for transportation applications. You can have larger or smaller values as well. All these three parameters, as I said, directly depend on the application as well as the motor type. So, number of phases. So you can have a single phase, two-phase or multi-phase motor, but the standard one is the three-phase machine, which is the common one in most of the applications. Number of poles for now, let's assign 4, but in applications like electric vehicles, this can be usually around 6 or 8 poles. 4 is a bit small for that kind of applications. Again, this is application dependent parameter. Then we have number of slots. Let's say for now 24 slots. Air gap thickness. This is a parameter that you have to provide for initial sizing. Otherwise, the initial sizing cannot be done. However, during the optimization process, we can tune this parameter because it's really important. And again, depending on the motor type, this can vary a lot. For example, in induction motors, generally the air gap thickness is smaller than that of permanent magnet. However, we can have large air gap thicknesses in induction motors as well, depending on the structural integrity of the design. For now, let's say 0.5 millimeter, which is the default value of the software. Ambient temperature, we have 20 degrees. Motor aspect ratio, as you can see the explanation here, motor aspect ratio is the stack height divided by the motor outer diameter, right? For example, in control applications, this ratio can be large, or for in-wheel traction motors, electric motors which are basically placed inside the wheels of an electric bike or electric vehicle. This ratio is very small. So again, it's an application dependent parameter. The other two, maximum outer diameter of the motor, this is kind of constraint that you can place. It is problem. But depending on the space, available space in, for example, inside a wheel of for example, of an electric bike, you can actually limit the maximum outer diameter. But for now, let's set it as it is, unlimited and maximum height. So the only constraint that we place is the maximum motor aspect ratio. You can have, generally, you can have two types of rotor location, interior and exterior. Exterior rotors normally have larger torque levels. This is the technology that, again, can be used, for example, in in-wheel applications, because in in-wheel applications, usually it's the rotor which is, we have exterior rotor that is connected to the wheel and rotates. But the most common one is the interior rotor type. So let's deal with interior rotor type, which you can find in most literature. So rotor type. In terms of rotor type, for brushless DC motors, we have several types of rotors, as you can see here. Can you see the types here?
Yeah.
Okay. So the simplest one is the surface mounted with radial magnets. The design can get more complex by adding different permanent magnet shapes or even different orientations of permanent magnets. You can have a spoke type magnet, or let's say IPM, interior permanent magnet designs with different templates. These are the most, this one is the most complex one, the 4-layer IPM motor with angle barrier, the most complex one that you can have in MotorSolve in terms of geometric parameters. You can also have magnet-free motors, which are basically called synchronous reluctance motors, where the torque is purely reluctance torque. You don't have any torque produced by permanent magnet. For now, let's deal with one of the general and simple ones. For example, this one, IPM with variable orientation magnets, okay? You can set the magnet material, which is very important actually. The material in an electric motor is very important, and you should be careful about selecting a proper material, which again depends on the application, motor type, as well as the environment that the motor is going to be used in. For example, in high temperature applications, let's say aerospace applications, when the temperature goes high up to, I don't know, 300-400 degrees, most probably you don't really want to use permanent magnets, because especially the conventional ones, because they can get demagnetized easily at high temperatures. So those are the points that you need to take into account. But for now, let's choose one of the most powerful permanent magnets, which is neodymium iron bore. You can have other types as well, alnico, which is usually used in flux switching motors, or samarium cobalt as well, or the other types. But one of the best ones is this class, neodymium iron bore, with different actually remnant flux density levels or coercivity levels, as well as permeability levels. So for now, let's deal with this one, 3231. You can also set parameters of the stator. Yeah, exactly. So you can have different slot shapes here, as you can see. So normally people use a square shape for common applications, but in some applications like induction motors, you can have, for example, this parallel type as well, which is usually used in applications that where you have, as I said, induction motor as the prime mover of the system. But for now, let's deal with this one, stator type. Okay, we're gonna use this one, a square shape, the simplest one. Okay, a stator coil material, which can be copper, any kind of good conductor like copper or aluminum. But in a stator, we most of the time use copper. However, if you have a squirrel cage induction motor, in the rotor you can also use aluminum as well instead of copper. It's die-cast aluminum. So there is sizing method here, which I'm not going to go into details of it. I can refer you to a book which is written by Professor Tim Miller and Jim Hendershot. You can find all the details about the sizing there. But for now, let's say that we have two sizing methods. One of them is based on the torque per unit rotor volume, and the other one is rated current density, right? So let's choose the first one, the first approach. You need to set a couple parameters here for the sizing, and there's a guideline here. If you choose torque per unit rotor volume, you have to enter the value of the torque per unit rotor volume. And the guideline says that, for example, yeah, here, look at this part. If you have neodymium iron bore motor, this value can range from 14 to 42, but you don't really know which value to select, right? Because this parameter is usually tuned during the optimization process. So you can set an average value here, let's say something like 25, for example, and see what's going to happen. But note that these values mentioned in this guideline are useful for conventional motors. If you have a very specific applications, this guidelines may or may not apply, okay? So that's why people do optimization after the sizing stage. And that optimization is going to be based on finite element solver, which is detailed and accurate enough. So, but for now, to get a rough initial design, we have to use this initial sizing. So the point is, the more accurate your sizing stage is, the less effort you need to put on the optimization. Yes. So for now, let's set 25. Coil fill factor, again, it depends. This one depends on the winding topology. If you have fractional slots winding layout, you can probably increase this to very large values, but for the classical layouts that are available in MotorSolve, 40 is a good value to use. Rotor aspect ratio, you can also find the definition of each parameter here. It's very useful actually. If you don't really know what coil fill factor is, you can read the definition and search for the keywords in the literature and find more about them. Rotor stator ratio, which again says that the outer diameter of the rotor divided by the outer diameter of the stator. Let's leave it as it is, 0.55. A stator flux density. This parameter depends on the material, silicon iron material that you use in your motor as the core material of the stator and rotor. The conventional materials like M19, for those kind of materials, 1.2 Tesla is a good value, but there's this recent material which actually whose flux density can go up to probably 1.5 or 2 times that of the conventional ones. So if you can access that new material, you can set this value to probably something around 2 Tesla. But 1.2 Tesla, which is the maximum allowable flux density in a stator, is a good value. So just leave it as it is. Back EMF limit is 0.9. Again, these parameters can be tuned during the optimization process as a constraint or as an objective. So, or even as a design parameter, it depends on the nature of the parameter. So magnet air gap ratio and also magnet coverage, this depends on the rotor type that you use. If you, for example, use surface mounted with radial magnets, you would probably have more magnet coverage. However, if you use IPM motor, like the one that we have used, the effective magnet flux density that goes from rotor to the stator, and basically magnet coverage will be smaller. So again, it depends on the rotor type as well as the sometimes as well as the shape of the permanent magnets as well.
Okay.
So we have entered the parameters. You can, as I said, you can use the default values, or if you are expert, you can set the value that you want. For example, in terms of the air gap, the expert designers know very well how much the air gap would be, not the exact value, but the reasonably acceptable range. So we have entered the parameters. If the sizing, now we're gonna apply all the values and see if the sizing works. If not, it will return an error and says that the parameter is not suitable. So let's see, if we get the sizing right, we will be able to observe the outputs, which is the case now, right? We have the rated current here for the size machine, outer diameter of the stator. As you know, we didn't limit the outer diameter, right? So it can be anything depending on the other values or parameters that we have already entered. However, if you limit this to something that you want, the sizing may or may not work. For example, if you said, I don't know, 10 millimeter, for sure the sizing wouldn't work because that kind of a small motor wouldn't be able to provide 100 Newton meter of torque. So that's one of the constraints that you can play with. So we can also have a stack length, air gap, diameter, and the other parameters as the output of the sizing. So as you can see, the sizing is done.
Wahid, I have a question.
Yeah, go ahead.
All right, so the diameters and the height that we're talking about, all of these are in inches, centimeters, meters?
These are millimeters, as you can see, the stack height in millimeter, okay? The convention here is millimeter.
Okay, perfect.
Yeah. So this is the motor that we come up with, right? So by a stack length, I mean the length from one end to another end of the motor. And we always assume that the stack length of the stator and rotor are the same, as you can see here. However, sometimes you can apply rotor overhang, which means that the rotor can, two ends of the rotor can actually come a little bit outside the stator. That is usually used to decrease the leakage flux of the stator winding, to provide a better coupling between the stator and rotor, and also deal with thermal issues. However, for standard machines, it's not the case all the time. So we have the stator back iron, right? Here's the stator structure. I mean the circle with windings in it. And this gray core is the rotor core, and we have the north pole, the red ones, and the south poles, the blue ones. So we have a 4-pole machine, as you can see here, right? 1 pole, 2, 3, and 4. This is, if you click on this panel, on the design panel, if you click on prototype design, you can see the parameters that you have already set. If you click on general settings, again, the same parameters, you can change the, let's see, yeah, you can change the air gap and other parameters here as well after sizing the machine, and you can observe the change in the design. Let's give it a try and see if it works. For example, instead of air gap of 0.5 millimeter, let's say 2. Did you see the difference?
Yeah.
Okay, that's the way you can actually use these panels to change the parameters, and then run simulations for the resized machine and see what happens to the outputs, like torque ripple, efficiency, and everything. So for now, those values are good because we don't really know the exact optimal value that can be tuned during an optimization process, as I said. But let's go through the other panels one by one and see what we've got here. Are you guys familiar with the skewing? Okay, skewing is basically, let me show you that. In terms of the rotor, when we talk about the skewing, it means that we kind of make the permanent magnet skewed along the stack length, like this.
Okay.
Let's reduce the transparency of the stator core to make sure that we can see the rotor. Let's go back to the rotor panel. Okay, you can see the rotor only, right? And now let's apply skewing. The first parameter, skew, as you can see here, sets the angle that the rotor is skewed over the stack height in a stator slot pitch. What is a stator slot pitch? Let's bring it back. Let me explain it first, and then we can talk about the skewing. Stator slot pitch is the angle from the middle point of one slot to the adjacent slot, okay? In this case, we have 24 slots, and so we have 360 degrees divided by 24 to 15, right? 15 degrees is your slot pitch. So you can either set a skew angle as, for example, 1 slot pitch, which is 15 degrees, or set the skew value as 1 slot pitch or 2 slot pitch. or whatever you want, okay?
Okay.
You see the rotor shape?
Mm.
Okay, let's set the transparency of the stator to 0 again. Okay, let's go back to the rotor. Okay, and now you can see the permanent magnets, right?
Mm. Yeah.
Now let's set it back to 0. You can see that if I set it to 0, this will change to 0 again.
Mm.
And the permanent magnets are basically directly
Straight.
aligned. Yeah. So this is called skewing, and that skewing is used when you want to reduce the torque ripple of the motor, but you should be careful. The more you increase the skew angle, the more you decrease the torque ripple, but the average torque will reduce as well.
Okay.
That's the problem with the skewing. So there's always a trade-off between the average torque and the torque ripple. So because I would say always we want to increase the average torque as much as possible while decrease the torque ripple as much as possible. So those two parameters, actually performance parameters, can be the objectives of your optimization. So skewing can be applied to both the rotor and the stator. In terms of the rotor, we apply skewing to permanent magnets. In the stator, we do the skewing for the slots, okay? Now let's reduce the rotor transparency. Something like this. Let's go back to the stator. Okay. Again, let's apply one slot pitch. Okay, the skew of one slot pitch. Did you see the change?
Yeah.
Let's make it 2.
Mm.
They both have the same effect in terms of average torque and torque ripple. What it does is basically to reduce the harmonic components of the motor torque. But not only the higher order harmonics, which are undesirable, are decreased, the average torque is actually reduced as well. So yeah, let's bring it back to 0. We don't want to deal with the skewing right now. So as I said, you can apply the skewing to rotor and a stator as well. If you have an induction motor, instead of permanent magnet rotor, you will have an squirrel cage or round rotor, right? In that case, you can again apply skewing to the slots of the rotor, not just the slots of the stator.
Okay.
So, for example, if you have a wind turbine high aggregation, which is actually a double fed induction motor or generator, there you will need to definitely apply skewing to the rotor or stator. Don't apply skewing to both the rotor and the stator. One would be enough. So in terms of the rotor, you can set the number of magnets per pole. Let's make it, for example, 2. As you can see, at each pole, you can have 2 sets of permanent magnets, but it doesn't change the number of poles, okay? 1 is the standard value. Let's keep it as it is. Okay, rotor overhang, that's what I was talking about earlier. Let's set the overhang to, I don't know, 10 millimeters. You see, the rotor length is larger than that of the stator now, right?
Yeah.
And you can see that in this view very, very well. Let's make it 20. So this is one parameter that you can use during your optimization. Okay. Now inner diameter of the rotor, which is basically the diameter of the shaft. You can also change that. to something like, I don't know, 50, whatever you want. Outer diameter can be adjusted as well. Bridge thickness can be adjusted. Let's zoom in a little bit. Okay. Oops, sorry. Okay. Bridge thickness is this small distance here. So let's make it, for example, 2 millimeters.
Okay.
Quick width. And all these parameters can be adjusted. But the good thing with MotorSolve is that it handles the geometric constraints automatically. For example, if we apply, I don't know, a very large magnet width, for example, right? Now it's 24 something. Let's make it, I don't know, a super large value, 400, right? It will give you an error and says that magnet width is not feasible.
Okay.
So that's the kind of constraint that is handled automatically in MotorSolve. However, I would suggest that you always, during your optimization process, because once you want to do optimization, you have to use MATLAB or Python or VB to automate this parameter changing, right? To call MotorSolve, automatically change the parameters and everything, not manually like what I'm doing here, right? So because you need to do this for several thousands of samples. So there I would suggest that you handle the constraints beforehand of running MotorSolve, so that make sure that your design will be feasible, because sometimes it's not easy to deal with this constraint, automatic constraint handling of MotorSolve during the optimization process. So if you do the constraint handling beforehand, that would be amazing. So yeah, these are the parameters that are available for this specific type of rotor. If you change a rotor type, you will have different numbers of parameters here, right? For example, instead of one layer, if you have, I don't know, 3-4 layers of IPM, a permanent magnet, you will have more number of design parameters here to work with, okay? So then we have the stator panel. We discussed skew and its effect on the geometry. We have the inner diameter of the stator, which is basically this radius from here to there, this point. Outer diameter, I think if we change the outer diameter, I'm not sure about that. If we change it, I think all the other dimensions will be scaled as well. It's not a dependent, an independent parameter. Let's see. Now it works now, but I think in the design page, let's change the outer diameter to 300. Yeah, if you change it in the design page, general setting page, it will scale all the other parameters as well.
Okay.
But in the stator panel here, if you change the outer diameter, it's a totally independent parameter, so you can change it freely. Again, you have the parameters of geometric parameters of the stator that you can play with. For example, let's zoom in. Stator slot opening width. Okay, we have an error here, meaning that 5 millimeters is too large for this slot. Let's make it 0.5, for example.
Okay.
And also the other parameters you can change. One of the most important ones is the slot depth, which greatly affects the stator losses, as well as the, you remember in the sizing stage we had flux density level 1.2 Tesla.
Yeah.
Okay, that's the maximum flux density that can pass through the stator back iron.
Okay.
If we make the slots depth too large, for example, 50, the state of black iron, this area will be,
This one.
yeah, it's very narrow, right? So the saturation will occur in this region and the stator will be highly saturated and the flux density level will most probably go beyond 1.2 Tesla, which is not good for the motor. That will increase the losses, core losses, and eventually decrease the efficiency of the motor. So this is one of the most important parameters that you need to set in your optimization process. So let's bring it back to its rated value. Yes, you can also change the other parameters. As I said, those are all available for you. Next, we have a stator winding,
Okay.
right? So this is the winding layout, which is the automatic layout of MotorSolve, right? You can have automatic layout or manual layout. If you are familiar with windings of multi-phase machines, you can use manual layout and set whatever you want. However, if you are not, you can use automatic layouts, which are basically the classical layouts available in the literature as well. And each different layouts have different values of a slot fill factor. The larger the fill factor, the better, okay, generally speaking. So the first one, which is 96.6%, is the largest one available here. You can use another layout, something like this. These layouts will guarantee that you have 4-pole machine. However, what is different between these layouts is probably the end winding length, as well as the harmonic components, spatial harmonic components produced by the winding, non-sinusoidal distribution of the winding. For now, let's stick with this one, the best one. You can have the connection type Y or delta. It depends on you and the application that you want to use, but most of the time we use Y connection unless otherwise. Drive type, sine wave, and 6-step. For design purposes, I would say sine wave is the best one. It will apply pure sinusoidal waveform to your finite element analysis. Number of parallel path is also available in the stator winding. It depends again on the winding layout. If you want to know what it is, you can read the explanation here or go dig into literature and find about it. Diode, these are the values: diode voltage drop, switch voltage drop, which are typical values and they are basically the unit code. You can set it to 0 to actually use an ideal diode or switch. Pwm methods, 2 types of Pwm methods are available: current hysteresis and space vector modulation. I would suggest that you use current hysteresis because based on my experience with MotorSolve, it's better than the space vector modulation here. However, MotorSolve has a very good capability, which is basically MotorSolve plugin for Simulink. You can extract your model as a plugin to Simulink and build your drive and control circuit in MATLAB Simulink, which is very useful, and then connect it to your MotorSolve model directly and run the entire motor drive circuit there. Also, in terms of magnet, we also have plugin for Simulink. You can have the model in magnet and export it to Simulink as well.
Okay.
So some of the other parameters, okay, as you can see, the default of MotorSolve is a 2-layer winding. You can see 1 layer, 2 layer, right?
Yeah.
There's a gap in between, which is insulation. That 2-layer winding can have 2 topologies, side by side,
Okay.
over under. Over under is the most common one. However, if you have fractional slot winding layout, you will mostly observe side-by-side topologies instead of over-under. But for now, let's stick with over-under. So you can change the parameters of this winding layout. So for example, a slot linear thickness, instead of 0.28, we can have, I don't know, this value. Or maybe a little bit larger to, okay. Now you can see the change. Basically, this distance from the stator coil to the winding to the copper is called the slot linear thickness, right? Okay. As I said, you can change the other parameters as well. Winding layout, you can have winding type, lap winding. Okay, this is a good one. Lap winding or concentric winding. These are the two main types of winding that you can find in the literature, lap or concentric. In the concentric winding, the windings of the two adjacent windings here will have different winding pitch. One of them is this, the big one, right? The other one, the inner one, has 1, 2, 3, 4, 5 slot pitch, and the big one has 1, 2, 3, 4, 5, 6, 7 slot pitch length. However, in lap winding, the slot pitch will be the same. It's basically the same coil, which is repeated clockwise or counterclockwise. That's the difference that you can find in the winding layout. You can set the number of coils per set, coil span, number of layers. Okay, number of layers. This winding had 2 layers. You can set it to 1, right? This is up to you, but I would recommend to use a 2-layer winding all the time because it provides you with a better total harmonic distortion level. It will reduce the higher order harmonics, space harmonics. So you can also have phase offsets and everything. Number of turns is very important. While you are designing your motor, I would say that it's good to use this number of turns as one of your design parameters and try to change it, vary it, and to see the effects. If once you reduce the number of layers from 2 to 1, it is suggested to increase, to actually double the number of turns.
Okay.
To get the same level of torque. Also to guarantee that the voltage level is that we set initially in the sizing stage will be suitable for the motor. Because, for example, we set 400 volts, right? And that 400 will be distributed over each and every turn of the winding equally. If you reduce the number of layers by half, then and if you do not increase the number of turns, the voltage over actually across one single coil of the stator will be doubled, which is not good for the insulation, and most probably in practice the insulation will fade.
Okay.
So let's bring it back to 2 layers. 2 turns. Okay, you can turn on the animation as well. You can see the direction of the current here in the winding, right? This is,
Okay.
and now from this coil, it will go from this pole, it goes to the adjacent pole, and then again, NS, NS, and so on. Let's go to the winding chart. You can see the ideal back EMF waveform, which is obtained by the selected winding layout. If we change the winding layout, I believe that this back EMF waveform will change. Let's select this one. Okay, now it's changed a little bit. In order to keep record of what you are doing, you can use this button here. add to
To
report,
report.
right? Stator winding line to line back EMF, for example, layout 1, add. It will be recorded here in the report panel, right? If you do that, again, for another winding topology, winding layout, for example, the first one, the best one, and go to the winding, okay, come on. For example, this one. Okay, for example, this one. Again, add to report, layout 2. Now you can make a comparison, right?
Okay. Mm.
This is an interesting tool to make the comparison between different layouts, not just the winding. Whatever you observe in this page, which can be back EMF or even the results which are obtained from this result tab, you can record it in the report panel, I mean this tab, and then make the comparison for different design cases.
Okay.
Now we are almost done with the initial sizing and design, as well as material assignment. There is a table here, table of design information, where you can find the general information of the design in terms of mass of different components of the motor, the parameters of the winding, and almost everything that you need to know. If you go back to the winding page, you can also find the resistance values of the winding, end winding resistance, winding phase resistance, line-to-line resistance, and everything here. These are also very useful. In the material panel, you can set the, you can actually change the material type of the components of your motor. For example, rotor core material. For now, it's M19, but you can set it to whatever you want. That is available here. Or I believe that we can also define user material as well. Yes, here in the material panel, under this panel, there is user materials, right?
Yeah.
You can actually define a new material. For example, we are currently dealing with this 3D printed material, high silicon iron material. You can measure its properties and then import the values here and give it a new name to the material, and also assign the permeability and everything which comes from the measurements. For example, this one, you can set pH values at, let's say, 20 degrees, 0, 0, 100, for example, I don't know, 1 point Tesla, and you can basically build the pH curve of the material here and save it as a new material, and then go to this material panel and select it from this, yeah, from the list. So you can do the same for permanent magnets as well. You can set the slot linear type, which is here, it's epoxy resin, which increases the structural integrity of the stator and the winding. Also, you can set all the other materials as well. It's all up to you. You can change the materials during the optimization process. You can do the optimization process for one set of materials and then change the materials, repeat the process again, and see what happens to the objectives of your design. You can also set the thermal parameters as well. we have the housing. By housing, I mean this part of the motor. You have the dimensions of the housing, like the parameters of the stator and rotor, as well as the winding. You can change those of the shaft, housing, and everything. You can set the cooling system parameters. To be honest, I'm not very familiar with the thermal parameters because basically my main focus in my PhD was the electromagnetic design. But if you are interested, you can dig more into literature and find about them.
Okay.
Thermal materials are also available here, and you can use them. And I think we are done with the design panel, which gives you the flexibility to change the size and material of all components of the motor. So it brings us to the result tab, but first let me go through the documents that I've prepared, see if I'm not missing here anything. Okay. Okay, one good point is this. I forgot to mention. I think we can apply negative values here as well. Right. So in terms of a skew angle, you can actually skew the permanent magnet or the slots clockwise or counterclockwise. It's up to you. Negative value means counterclockwise. Okay. And I think, let's see, what do we have here? There are a couple of other things I would like to talk about. Let's see if I'm not forgetting it. Effective number of slots. Okay. Let's go to the results tab. Okay, this is where you can get all the performance parameters of the motor. From cogging torque, back EMF current, torque, to every performance that you can find in this list, as well as the thermal outputs, magnetic outputs of the motor in terms of the flux density and everything. Let's go through the tabs one by one. The first performance parameter is the cogging torque. Cogging torque is basically the pure reluctance torque of a permanent magnet motor when the excitation is 0. The range of cogging torque, I mean the value, is pretty much smaller than the average torque of the motor. However, it's usually called the torque ripple producing component of the torque, and it's caused by the permanent magnets. So if you don't have permanent magnets in your machine or any strong reluctance torque, cogging torque won't matter. For example, in induction motors, we don't talk about cogging torque at all. However, in permanent magnets, it's a very critical performance parameter, and reducing cogging torque should be one of the design objectives. So let's see how it works. In terms of cogging, okay, the background solver, the solver that is running background of MotorSolve is basically a finite element solver, which is using magnet as well. So whenever you run any of these tabs, it will run some stages of that finite element solver to get the results and report the results to you. In terms of cogging torque, we can we can specify a number of data points that will produce the waveform of the cogging torque. 24 is the typical value that you can use. It's the basically the default value of the software. So let's keep it as 24. Then we have a speed accuracy trade-off of the finite element solver. The fastest one, the 1 is the fastest and 10 is the most accurate. Yes, if you choose 10, it will, I believe that it will increase the mesh density and make some adjustments to make sure that the simulation result is as detailed as possible. However, for our purposes of this tutorial, we don't really need to deal with the most accurate model. And in terms of optimization, if you really want to perform an optimization routine, I would suggest use the speed accuracy trade-off of 1, 2, or 3. Don't go beyond 3. You don't really need that because if you choose 1, the results are not wrong. They are not detailed enough. However, in an optimization process, you don't really need a very detailed response. You only perform an accurate analysis for your final optimal design to validate it with experiments, if available.
Okay.
But for optimization, during the optimization routine, just use speed accuracy trade-off of 1, 2, or 3. Stick with 1 and run the simulation. To see the cogging torque, you need to push this button, view results. And as you can see, it will build the model, the finite element model. You see the progress bar. So step 1 of 25. Now it's running the simulation. 25 steps. And if I'm not wrong, yeah, if we increase the number of data points, it will increase the number of steps here. Okay. This is the waveform of the cogging torque that we get. You remember that initially we set the average torque of the motor to 100 Newton meters. However, here the cogging torque is less than 1 Newton meter. That's exactly what I said. Cogging torque value is very small. Actually, if we increase the speed accuracy trade-off, I believe that it will change the value. It will be more accurate and it will increase to probably around 1 Newton meter or so, or maybe less. But again, it's smaller than the average torque. However, this generates torque ripple in the torque waveform of the motor. So we will need to change the geometric design parameters or even the materials or whatever that can be changed in the motor structure in order to make sure that we get the smallest cogging torque possible.
Okay.
Let's choose the speed accuracy trade-off to 4 and increase the number of samples to 40, for example. So yeah, as I said, the number of steps increases and it basically runs the finite element solver 41 times, because there is an initial point which is at the mechanical location, mechanical position of 0 degrees. So that's why it's going to take a while. Yeah, this is the bottleneck of FEA-based, finite elements based solver. They are slow, as you can observe here, right? That's why running an optimization routine where you need to run the finite element solver for, I don't know, several hundreds or thousands of samples will be really overwhelming and time consuming. So you should be patient, to be honest. Unless you have some HPC platforms to run the finite element solvers, actually deploy the models on the, for example, on a cloud server and run them in parallel. That will be amazing. You can, once you once you observe the results, you get the results in this page. You can view data and also save the data in the Excel sheet. In an Excel sheet, I will explain that once we get the results. Okay. The waveform changed, but what really matters in terms of clogging torque is the peak-to-peak value. Okay. And you can get the results here, as I said, and export the results as an XLSX or CSV file, whatever you want. There should be 41 points on this waveform. Let's see what it gives to us. Toggle, we don't need that. Okay, these are the points, simulated data points. And what the software does is to perform, as we can see here, a linear interpolation between the two simulated points. So to be honest, you cannot really rely on the points, on the values here in between the points, because that's just a simple linear interpolation. However, you can increase the number of points so that you get better waveform, or you can export the data and then use another software like MATLAB or Python to perform a better interpolation, line interpolation, right? That's also possible. Sorry. Next, we come to back EMF. There's a couple of types of solvers in MotorSolve. One of them is Pwm Analysis, and the other one is the motion analysis. Motion analysis is the most detailed and accurate one. Pwm Analysis initially performs some sort of response surface method, meaning that it runs the solver, FE solver, for a couple of operating points of the motor, and then it fits an interpolation function to those points to get the entire map of performance map of the motor. And then it applies, for example, switching inputs, space vector modulation, or current hysteresis input to that performance map and get the results. However, as I said, it's a kind of response surface method, and it uses interpolation, which is not as accurate as running the finite element solver directly for all the points. So I would suggest that you use motion analysis all the time if you want to make sure that the results are really the ones that you would get from any finite element solver. And now let's get the back EMF waveform.
Okay.
Let's use the fastest method and view the results. Oh, it again runs 41 samples. We don't really need. You can stop the simulation while pressing escape.
Okay.
Come on. Okay. Let's get back to the previous page. Make it 24. 24 is actually a good and useful number to sweep a sinusoidal excitation. You can sweep a sinusoid very well using 24 over the sinusoid. Okay. So let's perform the analysis again. And I hope you are familiar with this back EMF, torque efficiency concept, flux linkage, and everything.
Yeah.
Otherwise, please go through the literature, and if you have any question, you can ask me later on. In terms of back EMF, you can also extract the harmonic components. I think we missed it. It should be in the design panel. We can get there again if we have time. If you want to see how this winding layout affects the harmonics of the back EMF, yeah, it's here. You see under stator winding
Stator
part,
windings.
you can get the back EMF harmonics as well, right? Which are basically normalized with respect to the fundamental harmonic. Once you change the winding layout, for example, to this one, you will get different harmonic levels. Okay, now harmonics, yes. It's a function of basically the winding layout as well as the number of slots. That's also very important. If you change the number of slots from 24 to whatever, 12, 36 or whatever, that will change the harmonic component of the back EMF. So that's one of the parameters that you need to reduce. The less the harmonic contents of the back EMF, the better for sinusoidal excitation motors. Let's get back to the result tab. View results. Oh, come on. It's not going to run it again. Oh, no. But once you run it and save the model, the results will be available all the time. So you won't really need to run the time atonement solver again. However, here we didn't save it, so okay. So this 41 is probably something else in terms of back EMF, or is it something else? I don't know. Let's see. So, as I said, try to use motion analysis all the time. PWM is also good, can be useful if you have, if you don't really have time to run motion analysis or you want to deal with PWM excitation. But in that case, I would really suggest that you kind of couple MotorSolve to Simulink and implement the drive and inverter circuit in the Simulink environment or whatever package that gives you the capability. So here's the back EMF waveform that you get from that motor, the initial sizing. Okay, we have the current. Let's set this to, again, motion analysis. Okay, here we can see the difference between the excitations of the stator winding in two modes, motion and PWM analysis. Let's see what we have in terms of current excitation. The point is that the solver in MotorSolve is a current fed solver. It's not voltage fed, so be careful about that. However, if you implement, now in real world, we have voltage fed motors, right? We don't have current fed. What we apply in terms of input is always the voltage. It's either a direct drive motor, direct fed motor, or inverter fed motor, right? So both applies voltage, and the current is a function of voltage and the load of the motor. However, the voltage-driven finite element analysis is very time consuming. So that's why it's not implemented here. It's basically current fed, and it's assumed that, as you can see here, the current is a pure sinusoid in motion analysis. In PWM analysis instead, it is either space vector modulated current or a current hysteresis approach. Since we initially, if I'm not wrong, initially chose current hysteresis, we can double check. It's gonna give us a sinusoid with a small ripples on it, which is caused by the hysteresis bandwidth. Okay, okay, you can see the ripples here, right? The current, the actual current, the red one, right, is not pure sinusoid anymore.
Yeah.
Right? So let's see, in the winding tab, yeah, we had current hysteresis. If you change it to a space vector modulation, I haven't used a space vector modulation, but let's see how it changes. Yeah, it changes like this. So it depends on you, but in MotorSolve, I would suggest that you stick with motion analysis. Then we have the torque view results. As you can see, it is run pretty fast because we already run this current waveform. Yeah, this is the same finite element result. Once you run the finite element, the MotorSolve for one tap, the results in terms of torque and the speed and everything for that specific level of current will be saved in the solver, right? You can set the current level. For example, it can be a percentage of the rated current, which is obtained here, right? Its rated current is 83, right? So it can be 100% of whatever, 50% of that current level, or you can enter the exact value of it, the real value. However, it's good to deal with the percentage because you don't really care about this exact value, 83.4. You just need to make sure that you apply 100%, 50%, or whatever you want. So let's make it 100%. Go back to the torque tab, right? Once you change the current percentage to, let's say, 50%, since this is a new data point, new simulation point, it will run the finite element solver again. For sure, the average torque will decrease because we have reduced the current level. Also, another important parameter, excitation parameter, is advance angle. So if you don't know what advance angle is, please go read about it. In permanent magnet and synchronous reluctance motors, it is very important. For zero advance angle, I'll show you the effect. I will illustrate that later on when we deal with instantaneous field values under this panel. However, for now, I would say that in permanent magnet motors, an optimal range of advance angle to get the maximum torque out of the motor it depends on the motor topology, rotor topology, and permanent magnet volume, but it can change probably from 20 to somehow around 30, 35 degrees, but let's say 30 degrees. And bring it back to 100. Okay. We run, okay. For 30 degrees and 100, we have an average torque of 35. If you change this to, I don't know, 60 degrees, the average torque will change, you see? It really depends on the motor, to be honest, okay? But let's make sure that we have motion analysis here. Okay, that was run pretty fast because, yeah, that ran pretty fast because we were using PWM. Yeah, that's the good point with PWM, that's the advantage. However, in motion analysis, once you change one of these parameters, if it's not already solved, it should take a while to solve the new point again. And PWM analysis, as I said, I think you cannot really rely on the results unless you make sure that you create the response surface very well. Let's see what's going to happen. So in terms of excitation, the percentage of the current as well as the advance angle are the two important parameters that you need to set during the simulation. Okay, now we have a new waveform. And as I said, you can change these values to get new waveforms. The other two performances, I mean outputs, torque versus speed and efficiency maps, to be honest, are really time consuming, specifically efficiency map, which takes probably hours to run. Okay, because let me show you something here. Efficiency map. By efficiency map, I mean something like this. Over the entire torque speed profile of the motor, let's see that, for example. speed, and torque. You run the finite element solver for several samples and then interpolate the results of those samples in terms of efficiency. To get this efficiency map or any other performance map, power factor map, advanced angle map, whatever you want, over this entire map, okay? However, to get this map, you will need to run, I think, at least 70, 80, 100 samples, meaning that it will take time, too long actually, to get the results of those simulations. We don't really have time to deal with that now. However, to give you a hint, you can set the current level, because over that map you will need to change the current level from, let's say, very small values, for example 20%, up to, for example, 200% with the steps of 20. And you will need to change the advance angle as well from 0 to, let's say, 90 degrees, whatever you think is suitable, with the steps of 5 degrees, as well as you need to change the speed, because the efficiency map or torque speed map is obtained over the torque speed profile of the motor. So it depends on you, but we have a code written by Hossein, one of our former PhD students. That code is basically a MATLAB code which handles this automatically and runs the efficiency map, gets the efficiency map efficiently. It runs the MotorSolve in the background. So if you really need that code, just let me know. I'll send the code to you. It's a very well written code, easy to understand and easy to read. So you don't really need to set the points here. It will do the adjustments and settings automatically for you. So let's go to the next tab. We have flux current. So you can, again, do the motion analysis, set the speed accuracy trade-off. So I think you're familiar with these parameters, so we won't go there. Let's see the air gap flux, for example, here. Yep. You can get the flux of the air gap of the motor, which is one of the important objectives. As you can see, this is the flux density and the unit is Tesla. You can increase the number of samples. It basically extracts the flux density of the air gap over 1080 points around the air gap. However, you can change it. You can reduce it, for example, 500 or whatever you want. But that 1000 is a good actually number to, in case you want to get the harmonic components of this waveform, which is also very useful in the design. 1000 is a good number to deal with. You can also have the Phasor diagram of the voltage, back EMF, and the current of the motor. Let's see. There's an important parameter here. FEA current ratio. Can you see this?
Yeah.
Why do we need to set this parameter? The point is, the electric motors electric machines in general are non-linear devices, right?
Yeah.
So there is always saturation. However, this Phasor diagram is obtained by running the finite element solver for one single saturation point. I mean, one single operating point on the Bldc curve. So you have to kind of specify that point on the Bldc curve, and by 1.4, it means that you set the input current of the finite applied to the finite element model to 1.41 times the rated current of the motor. If you change this value, which will consequently change the saturation level of the motor, you will get different waveforms here. However, these waveforms are not really, I would say that you don't really need to use them during the optimization process. Those are good for circuit-based analysis if you want to implement the circuits model of the motor. you will need to know the know the advance angle or the phase angle of the current, voltage, or whatever you need in terms of implementing the circuit model. Okay, the next tab is analysis charts, which gives you 4 options: motion analysis, which is the most accurate one, then PWM analysis, DQ analysis, and lumped parameters. Motion analysis is as I said, is the most detailed and accurate one. It will give you the waveforms of these performance parameters: torque, input power, output power, to source phase angle and rotor angle. Let's see the torque waveform, current waveform, and voltage waveform. And we want to see you can also, instead of waveform, you can get the time average or harmonic contents of whatever you have here. You can get the line quantities or phase quantities or both. Let's stick to line quantities. You set the peak line current applied to the finite element model. As I said, it can be a percentage of the rated current or the exact numerical value. You can set the advance angle as well as the speed. So these 3 parameters define the operating point of the motor: current, advance angle, and speed. And then these are the settings of the finite element solver. Again, for one single sinusoid, 24 samples will be enough. Set the periodicity to 24, to best possible, and leave the rest as it is. Now let's run. Since the model is already run for this operating point, 100% of the rated current and 0 advance angle, we already had the results, right? So we didn't really need to run the solver again. So it was pretty fast. Now you can see the time domain waveform of the torque. V is the voltage, the green one, and the blue one is the current. But the point is, the current is sinusoidal. And the torque is a sinusoid with ripples on it. The point is, in practice, it's the other way around. For example, if you have a directed line start motor, you just apply a 3-phase voltage to the motor, which is a pure sinusoid. And then it's the current which carry ripples on it.
Okay.
Right? And this is the difference. So you should be careful about that. I would say that you can, if you want to be more realistic, you can extract the current waveforms from experiments, some rated current values or levels, okay, which are real current waveforms, and then import those waveforms to MotorSolve or Magnet, perform the simulations using those real currents. I don't think if it's possible to do that in MotorSolve, but in Magnet, I'm sure you can do it. I have done that in my PhD. You can import current waveforms and run the current derivative, but with real current waveforms, not just ideal pure sinusoids. You can also have the other quantities, run it, and yeah, it's a bit easier, but you can always extract the results, the numerical values, and do your post-processing in MATLAB, Python, or whatever, wherever you want. Then we go to PWM analysis. So you can do it yourself. We don't really have time to go into details because I always believe that motion analysis is the best way to go. So PWM analysis, you can do it by yourself. You have many different quantities here to get as the output. Then you have DQ analysis where you can get the result of a DQ circuit, also lumped parameters as well. I've already sent you the manuals of MotorSolve and Magnet. These are all explained in details there. So please go through them and learn. Just one single thing. As I said, we have a nonlinear system, meaning that magnetically nonlinear, meaning that by changing the motor excitation in terms of current level, you will observe different inductance levels. see how LD and LQ, two inductances, will change if we change the current. Okay, let's see, let's say for example, list or, okay, if we list, okay, 100, or let's say from 20% to 200% with the step of, I don't know, 40, for example. Let's run the simulations and see how the inductances will change. That's exactly what I was talking about, because once the inductance change, it basically means that the motor parameters change and motor behavior will change. So here you can actually see the two decoupled LD and LQ. In practice, LD and LQ are not decoupled. They are highly coupled. You can actually, let's see if we have that here. One of Professor Lauder's students had published a paper on this. Yeah, here it is. As you can see, the flux linkages in D and Q axes are different and they are not totally decoupled. For example, the flux linkage in D direction is a function of both ID and IQ. So meaning that these two axes are not decoupled. So depending on a motor, it can be either coupled or decoupled. For pure surface mounted motors, they are kind of decoupled, but in terms of IP motors, the one that we are using or dealing with, they are not decoupled. They are coupled, and you should take into account the interactions of both axes. However, MotorSolve only gives you under this panel, only gives you the decoupled values. You have LD and LQ. LD, the red one, LQ, the green one. And as you can see, by increasing the current level, which is on the x-axis, the inductances will reduce, meaning that the saturation increases in the motor. That's one of the points that you need to be careful about during the design process. The next panel, the next tab, which is generator results, can be really useful, especially for high aggregation. If you want to deal with generators, you can use this tab. But the point is, you need to specify, you will find the exact type of the generators that you want to use in your studies, because we have a limited number of templates in MotorSolve. And even in the other commercial packages, such as ArmExpert developed by ANSYS, the templates are limited. You don't have double stator or double rotor topologies, which are normally used in wind technologies, wind turbine technologies. So unless you stick with one of the templates here and just try to prove the concepts using that templates, and say that the idea can be extended to new topologies if available. So in terms of the generating operation, you have different outputs. We know that in generators, we mainly focus on power versus speed, torque versus load angle. Load angle is one of the important operations, outputs. Voltage versus current, which gives you the stability of this generator and things like that. Again, you have motion analysis, reduced order model of the generator, DQ analysis, and a couple of more things. So if you are interested, you can go through this step, but I prefer to not to, because we don't really have time. But the menus and details are kind of similar to motoring operation, however, with a little bit of difference in terms of the outputs and performance parameters. Then it brings us to the thermal chart, where you can perform a thermal analysis. And the most important tab here is the temperature, where you can get the temperature of all the components of the motor that we have designed over a duty cycle. The duty cycle can be anything that you define. on this right side, you can set, for example, you can say that the first interval, the motor will operate with run for 15 minutes under 100% of load level and 100% of the speed all the time, and 5 minutes after the first interval, the second interval comes with for 5 minutes, zero load, and the speed, for example, can change, I don't know, from 100% to 50%. You see the waveform? You can also add another interval, 20 minutes, 50% of the load, 50% of the speed, and 50% of the speed again, right? You apply the settings that you want. Thermal analysis is really time consuming, can be time consuming depending on the maximum time steps that you apply, and some other parameters, and also the number of coupled iterations you see. I think if we increase it, it will take more time, but there's explanations here. So let's run it once and see what happens. Oops, sorry. It will give you the time-dependent temperatures of all the components. So if you at some points need to do thermal management of your motor or generator, you can perform this analysis as well. Okay. Now it's running. So why don't we get results here? Oh, we haven't selected anything. Or if okay, with control space, you can select all of them at the same time. Let's see if we can get the results. Okay, what's happening? Am I doing something wrong? Okay. Axis show, no. Okay, let's save this. And here, design one. And close it and open it again. You can do all this, as I said, using a scripting tool of MotorSolve. The same applies to magnet as well. One of the manuals that I sent you is about scripting, VB scripting, but it's easier to do scripting in MATLAB or Python. MATLAB is the best, I guess. So I can send you some of the samples of the scripting, and you can actually use them for your future works. Now let's see what the problem is here. Okay, run. Oh, it's a bit weird. Why don't we get anything? Temperature, no. Guys, any idea? I did that yesterday. It worked well, but now it's a bit weird. Let's see. I will try to get this work, and if I get something, I'll send you the model. So for now, but if it runs, if we can get it run, you will see that the temperature will increase gradually from ambient temperature, which we already set to 20 degrees, to a steady state value. And the final temperature will be different for different components that we select here. But I'm still curious why it doesn't work. Okay, number of carriage, okay. Maximum time step. Okay, let's see this if we can get the 3D thermal view of the motor. If it works, there must be something wrong, or we are doing something wrong. Oh no, why? No. Okay, let's get the cogging thing if we can. Let's see if we can get the magnetic results or not. That's a bit weird. You can do the thermal analysis here directly in MotorSolve, or export the model to magnet and couple that to terminate and then use it. But the thing is, I don't know why. Let's make this here and make some changes. Maybe it works. Come on. I don't know. Okay, let's pass. I will deal with that later and let you know the results. Okay, instantaneous field. You can have different quantities, flux density and flux function. Let's see what it gives us. It will run the finite element solver for the input for this excitation. For example, 100% of rated current and advance angle of 0 and rotor position is 0. Okay, this is the field distribution that you get. Okay, it's pretty saturated. This is not a good design. You see the rotor, the flux here is saturated. Wow, 1.94 Tesla. This is not acceptable. Maybe the model is wrong, or I hope it's the model which is not good. Okay. Yeah, this model is not acceptable. That's why we do optimization, okay? You see the flux does not even go through the rotor back iron, meaning that this part is totally useless and wastes the weight of the mass of the rotor. If you don't really use or pass the flux through the rotor back iron, so why do we even need to add that back iron to the motor? So you can definitely remove this part and reduce it, but to be honest, 1.94 is very bad, not acceptable at all. So
why is the
then let's see, flux density, current density. You can get the results of different values, different quantities, demagnetism, proximity, and stuff. But what I would like to do is to show you the effect of advance angle on the flux distribution. Let's get back to the winding topology, which is this. And as you can see, this line, this red dashed line, is the magnetic axis of phase A, right? This is phase A. And using the right-hand rule, you can get the magnetic axis of phase A, which is this. And in this figure, we have the magnetic axis of phase A right at this direction. And we have the north pole here, north pole of the rotor, whose magnetic axis is again in the same direction, right? If we set the advance angle to 0, it means that the value of IQ, the current component in the on the Q axis, is maximum, and that of the D axis is 0. And if we apply 90 degrees, means that we have a purely D axis current, and the value of Q axis will be 0. If we apply 90 degrees, the motor has to demagnetize, because in this case, the field, the magnetic field applied by the stator winding will oppose that of the permanent magnet in the same direction, which means that they will demagnetize each other. So let's run it for 90 degrees, which means that the IQ is 0 and ID is maximum. You see, the motor is demagnetized. The flux level decreases, and that is this concept called flux weakening, which is used in wherever you want to increase the motor speed beyond its rated or nominal value, which is the case, always the case in transportation applications like electric vehicles. For example, we already set 3000 RPM, right, as a rated speed. But if you want to go beyond 3000 RPM, a method which is called flux weakening is applied in order to weaken the flux so that the motor will be able to operate beyond 3000 RPM. And depending on the rotor topology as well as the permanent magnet volume, you may be able to operate over 5-10 times the rated speed, maybe 15,000, 20,000 RPM. We also have motors, ultra high speed motors, which operate over 100,000 RPM. So this is the technique that people use for to guarantee that they can get a high speed level. If we set it to something around 30 degrees, which is a typical optimal value for motors, we will get some sort of results, but with different, flux values with less actually magnitude, with lower magnitude, however, but different direction. But still, I'm not happy with this design because the rotor is super saturated. So as I said, we need to perform some sort of optimization to make sure that this saturation does not take place. So I guess, yeah, that's about MotorSolve. I'm gonna check this thermal part again, temperature analysis panel, and get back to you maybe later on. But for now, we have done the electromagnetic design. Let me check my list of my to-do list and make sure I've addressed everything that I wanted to. Okay. There's an option here called export. Okay, you can export this design to magnet, and also you can create a new design. Let me see where that's called. Okay, you can create a new design, prototype design 2. And you can have that design on the same panel, right? The design panel. So prototype design 1 and 2. You can add more designs and change the parameters and compare the results with each other. Kind of manual, handmade optimization process, yes. But again, it's not, it will be time consuming to do the optimization here directly on this panel because you don't really want to add thousands of designs to this panel and compare them one by one. So that's why we run the optimization algorithms. You can export, as I said, you can export the design to magnet. Okay. And let's go back to this. Okay, we have the magnetism model here. This is actually what is actually running in the background of MotorSolve to give you the results of motion analysis, Pwm analysis, DQ, or lumped parameter, okay? This is the same model where you have the rotor components, stator components, motion. Motion, yeah, in magnet, you should always assign a motion analysis or motion component. which consists of the rotor components as well as a part of the air gap. This is very important. To guarantee that we have a stable torque computation, we always discretize the air gap. This is the air gap, right? This part is the rotor and this part is the stator core. We discretize it to at least two parts, the rotor side and the stator side, but it's better to increase the parts. And if we select the motion analysis, as you can see, two components, two inner components of the air gap are assigned to the rotor and the other two are assigned to the stator. The inner parts will rotate with the rotor as we increase the mechanical position, and the other two will be fixed at their place. We do this in finite element solver or environment to make sure that we have a good torque computation. We also have the coils here, right? Coil A, B, C. If you right click on one of them, go to properties, you can find it. As I said, it's a current driven coil, right? It's a stranded. You can have solid coil or a stranded coil. A strand area is specified here. These are all exported from MotorSolve. Also, the excitation here, which is sinusoidal excitation, the magnitude. Don't get confused. This V is not voltage. That's basically the input. I'm not a fan of this terminology here because it's kind of confusing. People think that it has to be voltage here, but it's not. It's a current driven model. So I would suggest that maybe Infolitica should change this at some point. But the magnitude is 100 something. You have the frequency, which is 100 hertz, as well as the phase shift, which is 180 degrees for phase A, phase B, and phase C. Also, if you go to the motion part, it's velocity driven, right? We have fixed the motor speed. It's not a load driven. If you have a voltage driven model, which is kind of the real case, right? When you run a motor, when you test a motor in reality, it has to be a voltage driven model. It is a voltage driven motor. It has to be load driven as well, because you just connect the load to the shaft and run the motor, and the speed is a function of the supply frequency. And if it's an induction motor, it is also a function of the load as well. So, but in this case, since we have a current driven model, it has to be velocity driven. We deal with velocity driven model, and the velocity, okay, let's see, position. Okay, there is something with the MotorSolve model, something wrong, because we don't have the velocity here. I don't know why. There should be velocity in terms of position or speed. That might be the problem, that the thermal model didn't work. Let's extract the other one and see, or create a new order. Let's extract this one. I don't know why this is happening. Let's go to the motion. Okay, as you can see, there should be velocity once you extract the model. I don't know what's going wrong with the other model, but we can deal with this one. Let's see if we have excitation here. Yes, yes, yes. Okay, we have everything set, and now we can solve the model. You have different types of solvers here. I'm going through the options that you have quickly, because I would like to set up another meeting to explain the magnet from scratch. So, but for now, just let us stick with this one. What we need is a transient 2D with motion. You can run the model in 3D, but of course it will take too much time. Basically because of the number of elements that you need to deal with in 2D. Okay, this is the mesh structure that you get from magnet. You can change the mesh density, increase or decrease it at different components. But once you deal with 3D model, as you can see, you have different larger number of unknowns which are not easy to solve. I mean, it's time consuming, takes too much time. So in symmetric motors, I mean, where the motor is symmetric in the z-axis, I mean, the structure doesn't change on the z in this direction, I mean z direction. You don't really need to run the model in 3D unless you want to perform a thermal analysis. In that case, end winding effects become really important, meaning that you have to run the model in 3D. But for electromagnetic simulation, for this kind of motors where there's no skewing effect or something like that, 2D is enough. You run the transient 2D with motion because we have the motion operation here with constant speed level. You will get the same results as you get in MotorSolve in terms of torque and everything. But to be honest, MotorSolve makes the life way easier because you don't really need to set the mesh density, the solver properties, motion analysis. In terms of motion analysis, yeah, you do something, but in general, no, it's just automated. It automates the process. But here, in magnet, you have more flexibility, but you need to know what you are doing. You should make sure that you set the settings and adjustments correctly. Okay, now it's run. First of all, there's a tab here which is called Field, Problem ID 1. We have the solution of all the time steps over that motion analysis from 0 to 30 milliseconds. You can get the distributions like flux function if you update the value at the first time step. This is the case you have. This is the flux function. And the last time step, this is it. And somewhere in the middle, this is it, right? And you can have shaded plots, for example, B normal, something like this. Or also, you can get the distribution time average, for example, hysteresis loss values on the motor structure. And there's another tab called Results, which gives you the global results of the motor. You can get the time domain waveforms of energy, force, flux linkage. You have a three-phase machine, right? So there are three flux linkages, A, B, and C. You want to plot them over one plot. So let's graph. This is the flux linkage of coil A, B, and C. You get the numerical values here of phase A, right? And you can also extract the data to a CSV file or text file. Let's get back to this. You can get the force applied to the rotor body and the stator body, force and torque, right? And as you can see, torque is in the z direction, which should be the case because we actually run the model in 2D and the current is in the z direction, so the torque has to be in that direction as well. So if we update the value, sorry, we had to do this. This is the torque level. We can get the average value or torque ripple, which is usually the peak-to-peak torque component. Also, we can get the ohmic losses of the stator coil. We can get the iron losses as well of the stator. And in the ohmic losses, okay, the permanent magnet loss is located here as well, surface mount with permanent magnet. Okay, this is rotor core. So why don't we have the permanent magnet losses? That's also weird. We used to have that under ohmic losses. Professor, are you there?
Yep. Yeah.
Has Infoletica made any changes to the conventions of the global result tab? Because there used to be permanent magnet losses under this tab, ohmic loss.
They haven't. I'm just wondering which version of the software we're running here, because this is
Don't have
certainly yeah, certainly this is quite old compared to some of the versions. So I'm just wondering whether so I don't know why it's not showing.
Yeah, but I'm I'm pretty sure that there should be some losses here about permanent magnet.
Well, it depends. You have to look at the permanent magnets. If there's no conductivity associated with the permanent magnet, which means the possibility there would be no eddy current losses in it.
Oh, maybe.
And so it's possible they're not showing any because there's no. So you know, if it's possible the MotorSolve and what condition it was running set the permanent magnet conductivity to 0. So yeah, you're probably right. It should be there, but if it's zero conductivity, there won't be any losses, so it's not showing them.
You're right.
I think that's what's happening.
Yeah, exactly. But any idea about that temperature analysis in MotorSolve?
No, it's a bit weird. I want to go back and look at that.
Yeah.
But as you say, there's something wrong in the excitation waveform, because I noticed on the temperature analysis it should have been time stepping through the cycle, and it wasn't.
Yeah.
It was aborting early on, so I'm not quite sure what was going on there.
Okay, check. Thank you. Okay, let's move on. Yeah, as I said, you can get the motion quantities here as well. The good thing, the very interesting thing with magnet, which I'm going to explain in more details in our next meeting, is that you can implement the design from scratch. You can draw all the lines, curves, and everything, assign materials, excitation from scratch. But as I said, you need to know what you are doing. And there's an interesting tool here called scripting. Whatever changes you apply to the model, let's say, if you draw a line or whatever, change excitation, you can record the script, which is in VB language, and then use that later on if you want to make the process automated. Let's plot a line here or change the excitation, for example, or maybe the number of turns to 15. Okay, and stop recording. This is the VB script that you get from that action we just made, right? So you can just copy this in any basically scripting tool, or in MATLAB we use invoke function to call this these lines and perform the design in an automatic fashion. So I'm going to explain this scripting tool which is, as I said, very useful in our next meeting, maybe probably next week if you guys have time. So for now, I think that would be enough. We went through MotorSolve, but if you have any questions about MotorSolve, please let me know. Any question, guys?
Yeah, I actually had a question regarding the electrical angles. When you had shown us the winding charts,
Okay.
I think the x-axis was an electrical angle and it was comparing something else. I was trying to visualize what that exact value we were looking at.
This one?
Yeah.
It is electrical angle.
Right. So technically, does it have to do anything with the rotor angle and the stator angle's difference? What exactly does that indicate?
No, this is electrical angle, which corresponds in this case to one pole of the machine.
So it's the angle of the waveform itself. I think the phase angle.
It's the phase angle. This is not the difference between the rotor and the stator.
Okay.
Yeah, you should be careful about that.
Yeah. Okay.
Yeah, that's actually a good question because if you guys know, electrical and mechanical angles are different. So electrical angle is always larger than or equal to mechanical angle of the motor. So anything else?
Also, is it possible to export the model from MotorSolve and then call it in MATLAB and I don't know, use MATLAB to have a hardware in loop? So what I have in mind is,
Yeah.
Make a prototype outside and connect it with MATLAB. And while MATLAB is solving something with respect to the prototype, the hardware itself, I want MotorSolve to run in background and try to figure out the temperature and the electromagnetic properties.
I think Professor Lauder can answer that better than me.
I think what you're talking about there is what we call co-simulation, and you can co-simulate with Simulink and MotorSolve, so or certainly with Magnet. So so the two run parallel. So Simulink, when it needs information, asks the Magnet model for the data. So that will work. There's also a variant on this where you can export a response model of the motor to Simulink, and that just becomes a block in the Simulink circuit. So there's two ways of dealing with that within the system. It's kind of, I think that's the advanced guide. We can, Vahid's done a terrific job today of skating through MotorSolve and giving you some idea of how to design a motor using it and what the characteristics are and so on. And he's going to do it for Magnet. And then there's the sort of, once you guys understand this, we can go to the advanced guides where we start talking about co-simulation with other systems, as he says, using VB scripting to talk to other systems. There's a whole stack of capabilities in there, which I think will do what you want to do if you want to model an entire drive cycle with a motor attached to it. It's all doable. In fact, Vahid has done this, I think, so he knows how to do it.
Perfect. Thank you so much, sir.